Hello, my name is Jordan Jones, and today I will be solving this homework problem from homework 3. And this is my ID just for confirmation. But yeah, this is homework 5, or homework 3, problem 5. And the question asks us to derive an expression for V out of t for t is greater than 0 in terms of R1, R2, R3, C, and A. And then we have a part B over here. A is the unit step function. This is an op-amp problem, so let's get started. So first thing I'm gonna do real quick is label our nodes and our currents. So this current we're gonna call I1. This current going this way is I3. And this current is the current across the capacitor. And I've labeled our nodes as well. This is V out. This is the unit step function, or our V source. This is our virtual short, so the voltage here is 0. So after doing a KCL at this node, I'm going to go ahead and write the equations over here. So this right here is IC. So IC, the current across the capacitor, is equal to its capacitance times dV dt, where V is equal to the voltage across the capacitor, right? So if we look at our capacitor, the voltage across the capacitor, the positive node is at 0 volts, and then our negative node is at V out. So that's why we have this 0 minus V out right here. And then we have the derivative operator, d over dt. This is I3, or not I3, sorry. It's going to be 0 minus V out over R3. And then our last current is going to be 0 minus V source, or 0 minus V in, I believe, over R1 equals 0, right? So once we have this equation, we can go ahead and start doing some rearranging. All I did was get rid of the 0, took this negative and put it outside. So kind of just basic algebra. Negatives on the outside, C dV out dt. And this is the derivative of V out with respect to time, right? This right here is just V out over R3, again, negative V out. And then this term is exactly the same. We have a negative V1 right here. So I just got rid of the 0 and we get this. So for the next step, I'm just going to do some rearranging. We're going to add V1 or VI over R1 to both sides, and we get this. And then everything else stays almost the same. We're going to go ahead and divide both sides by negative C, right? So we get this leading term by itself. Flips the switch of this to positive 1 over R3C. V out equals V1 or V source over R1 source negative, right? So this right here is the form of a standard, I believe it's called a linear ODE, a linear ordinary differential equation. So we have our x prime, which is essentially V prime, or V out prime in this case, V out prime. And then we have a constant A. Remember, 1 over R3C is a constant multiplied by V out, which again is playing the role of our X term. So that's these two. And then we have one more constant, which is B. So this is the form X prime plus AX equals B. This is the form of an ordinary ODE. So I'll write that one more time. Plus AX equals B. Right, so this is the form of an linear ODE. And with that, we can use this equation over here. So this equation is kind of like a shortcut, but essentially, once you get your equation in this form, you can go ahead and start plugging in values into this standard equation, right? So V out of 0, e to the negative AT plus b over a 1 minus e to the negative at, right? So this is an equation that is given to us in class. And essentially what's going to end up happening is this v out of 0 term is going to equal 0. And the reason behind that is because we have to remember this is a step function. And essentially what the step function looks like is we have an x and y axis, right? And before we hit 0, we're at 0, and then it shoots up to 1, and then it's going to 1 for essentially infinity, right? And this is 0. And the reason that our v out of 0 is 0 is because at t equals 0, yes, the equation is asking us for t greater than 0, but at t equals 0, the voltage spikes up to 1, but the voltage across the capacitor cannot change instantaneously. So remember, prior to the step, you can kind of think of it as a switch. The voltage across the capacitor is 0, but at the instant that the switch is happening, it will also be 0 until some time has passed. So this term is going to cancel out. This cancels out, and we can start plugging in b, a, and all that stuff. So our b term is again equal to this, a is equal to this, and if we go ahead and do some algebra, we can see that our b is right here. This is our b term, and if you remember, dividing by a fraction is the same. So say we have b over a and a is equal to 1/2, right? Dividing by a fraction is the same as multiplying by the reciprocal. So these are the exact same thing. So what I'm doing here is I'm multiplying b by the reciprocal of R3, or the reciprocal of a, which is R3C over 1. And that's where this term is coming from. And then this follows the format of our shortcut. A is 1 over R3C. So this becomes T over R3C. And this is our general form, but we can do some simplification on this end, and we get this. So the reason that we go from here to here, if you notice, this capacitance and this capacitance cancel out, right? So we're left with V source over R1 times R3, right? This is what we're left with, right? VI is equal to A times the step function. And so that's what we're doing. We're just plugging in A U of T into our equation, and we did a little bit of algebra up here. And this is the answer to part 1. This is the general form, so we can go ahead and highlight that. In order to solve for part B, all we do is add in our terms. So C is 0.25, R3 is 2 kiloohms, R2 is 5 kiloohms, and R1 is 1 kiloohm. So if we go ahead and add that, we get these numbers. R3 times C is 0.5 because R3 is equal to 2 kiloohms and C is 0.25. The 24 is coming from our AU of T times R3 over R1 because R3 is 2 kiloohms and R1 is 1 kiloohm. So 2 kiloohms over 1 kiloohm equals 2. And 2 times A is 12. 2 times 12 equals 24. And that's where this is coming from. And remember, we keep our negative. That was here. And this is our final answer. There should be volts right here, I believe. Volts. But you get the point.